We're going to start off just a little bit different this morning with 3 multiple choice practice questions. I'm going to ask you to take out your phones, and I'm going to ask you to do questions 61, 62, and 63 separately, one at a time. Please submit number 61 first as multiple choice number 1. All right, let's take a peek at this now that most of you have responded. We've got an electric force on a neutral pith ball. Obviously, there's the electric force that's caused by the Van de Graaff generator pulling the neutral pith ball towards it. Student charges the Van de Graaff generator, suspends the pith ball by an insulating thread. So there's no conductivity between the pith ball and whatever this is, the ceiling, the roof, whatever it is. The question says, when the neutral pith ball is placed near the charged Van de Graaff generator, the pith ball is attracted to the generator as a result of what? Well, we're not told, I don't think, that the generator becomes either positive or negative. We're told that it becomes charged. Okay? We know, because we've used a Van de Graaff generator, that it becomes negatively charged. But even if you didn't know that, okay, even if you thought that the Van de Graaff generator was positively charged, the same basic analysis would apply, okay, except that the charge separation that we're going to see would be opposite, that's all. Van de Graaff generator is negative, let's make that assumption. The neutral pith ball, okay, we got some positives in that neutral pith ball. We got some negatives in that neutral pith ball. What happens to the positives in the pith ball? Well, they're going to stay where they are, right? What happens to the negatives in the neutral pith ball? Yep. Good. They're going to be pushed to the far side, or at least lots of them are going to be pushed to the far side. And that's going to leave us with a separation of charge. One side is positive, one side is negative. The side that's closest to the Van de Graaff generator is going to be oppositely charged. It's going to be positive, right? So that means that opposites attract, it's charged. You've got a neutral object that has a charge separation that's attracted to that negative object, all because of this induction, this charge separation, and opposites attracting to each other. So what's our answer here? Well, it sounds like induction works, right? It sounds like that works. Grounding, induction is a better answer than that, right? Conduction, definitely not. The other answer that people put was D, induction and grounding. Induction and grounding. I don't see any grounding there, right, guys? Sorry? Yep, absolutely. It's on an insulated thread, so it's certainly not grounded here, and it's not connected to anything else, so it's not grounded. I don't see any grounding there. It's just going to be A, induction. All right, related to the same diagram, I'm going to real quickly do multiple choice number 62. You can submit that one, please, as, once again, multiple choice number 1. All right, we want to find in that question the direction of the electric force on the pith ball. We've got responses from most of you, and most of you agree on the answer here. The pith ball is pulled towards the Van de Graaff generator. We know that for 2 reasons. We see a picture of it physically being pulled toward the Van de Graaff generator, but we also know that charged objects are attracted to neutral objects, and neutral objects are attracted to charged objects. So the pith ball will be attracted toward the generator. The generator will also be attracted with an equal and opposite force toward the pith ball. That's one of your questions on your assignment, right? You get 2 objects. One's got a lot more charge than the other, but they're both attracted by equal and opposite forces. Hey, can anybody explain to me real quickly before we actually answer the question at hand here? Why is the Van de Graaff generator not moving toward the pith ball? If it's attracted by an equal and opposite force, if the force on the pith ball is the same as the force on the generator, but opposite in direction, why is the generator not moving toward the pith ball as much as the pith ball is moving toward the generator? Yeah, the Van de Graaff generator is a lot heavier, right? It's like, I dropped this board marker toward the Earth. The Earth applies a force on the board marker, a force of gravity on the board marker. The board marker applies the exact same force of gravity on the Earth. But the Earth doesn't go up toward the board marker goes down toward the Earth. Equal and opposite forces, but the Earth is way, way heavier, so it would require a much bigger force to move the Earth than it does to move the board marker. All right, so these forces are equal and opposite. The force on the generator, again, is toward the pith ball, although we don't notice that force as much. The force on the pith ball is toward the generator. So the electric force would be this way. Okay, most of us put that. That's good. Okay, there was a couple of people that said the force on the pith ball was this way. It's not. That would be a repulsive force. Or maybe you found the force on the Van der Graaf generator instead. Yep. Yeah. Well, actually, no. That'd be wrong as well. If you put the electric field, knowing that the Van der Graaf generator is negative, although you're not actually told that in this question, okay, but you guys know that the Van der Graaf generator is negatively charged, then the record, the electric field would point towards it as well, right? All right. Okay, fair enough. Finally, I'm going to ask you to take a look at question number 63, which also goes with it, the last of our multiple choice questions, at least for now. Please submit that one as multiple choice number 1 as well. Time to take a look at this question now. We got answers kind of all over the place on this, which is expected for this question. It's a tough question. First time I saw this question, I got to be honest with you, I was thinking, what do I do? I'm not sure what to do. It's just a tough question. Okay, when the teacher's thinking, what do I do? Okay, then you know it's a tough question. It probably took me, I'm not sure how long it took me to actually solve this question, probably 3 or 4 minutes, which might not seem like a long time, but when you're the teacher and you've gone through Physics 30 a lot of times, that's a long time. 3 or 4 minutes is a long time to solve a question. We want to find the magnitude of the electric force on the pith ball, and I don't know about you, but when I saw this question, the first thought that came to my mind was, well, you want to find any electric force between the pith ball and the Van der Graaf generator. Let's use this equation, right? F is equal to KQ1 Q2 over R squared. How many people had that first thought? Use Coulomb's law, F is equal to KQ1 Q2 over R squared. Okay, that's exactly what I thought, guys. Exactly what I thought. But then I'm looking at it and thinking, well, A, we don't know the charge of the pith ball, and we don't know the charge of the Van der Graaf, and the pith ball doesn't even have a charge. So I can't really use that. So then I thought, well, what's another equation for electric force? Well, we know that the electric field experienced by the pith ball would be the force over the charge. So maybe if I know the electric field experienced by the pith ball, I can turn around and multiply the charge by that electric field to get the electric force. The problem I have with this is, again, the pith ball doesn't have a charge. The electric field strength, we don't know what it is, and we can't find the electric field strength without knowing the charge of the Van der Graaf generator, so that doesn't seem to work either. Any equation I have with the electric force in it doesn't seem to work. Here's the difference between you and me, okay? Or between lots of you and me. It's not that I'm smarter than you are. It's the difference between lots of you and me is that when I see a question like this, even if I have a tough time with it, I'm not scared off. I'm not going to panic about this question. I'm confident that I'll get this question right. Or whatever question that I see, I'm confident that I'm going to get it right, regardless of whether I know how to do it right now or not. And guess what? Because I'm confident I'll get it right, I usually end up getting it right. So I see this question for the first time. I don't know what to do, but I'm confident. I start trying things. I start trying valid things, not just random things, but valid things. Okay? I thought, all right, well, what do we got here? We got a pith ball that's being pulled toward a Van der Graaf generator. We already looked at the direction of the electric force. Let's just draw that electric force in since we solved for that value already. Or sorry, we not solved for the value, but we got the direction of the electric force already. Well, then I said, well, look, there's also a gravitational force acting downwards on it. And look, there's a force of tension in that string pulling up like this. And I did this not because I knew where I was going with this, but just because it was the only thing I could think of to do. It was something. It was valid. It wasn't necessarily going to lead me to the answer, but it was a valid thing to do. Draw the forces acting on it. Doesn't help? Doesn't help. Hey. Whatever, I'm no further behind, right? But this is where it occurred to me. This is when it clicked to me. When I had this drawn, not before I drew it, but after I drew these forces, it clicked, wait a second, I think I can solve for that electric force now. Not using KQ1 Q2 over R squared, or E is equal to F over Q, or any of those equations. I know the force of gravity acting on this pith ball is 2.5 times 10 to the minus 4 times 9.81. There's got to be a reason why they give us the mass of the pith ball, right? I mean, it's possible that they just give it to us just to throw us off, but usually it matters. So stands to reason that If it matters, I'm going to find the force of gravity with it. Let's do that now. What is 2.5 times 10 to the minus 4 times 9.81? Let's go the unrounded number. I think it's 2.45 maybe. 2.4525 times 10 to the minus 3 newtons. All right. That's all I have, though, isn't it? I have an angle as well. 20 degrees up there with the force of tension. If this pith ball isn't moving, then the forces have to be balanced. If it's not moving, then the force to the left must balance the force to the right. Well, the only force that I have to the right is the x component of the tension. The downward force has to balance the upward force. Well, the downward force is gravity. The only upward force I have is the y component of the tension. I know the y component of the tension. It's the same as gravity. I just solved for that. So the y component of the tension is 2.4525 times 10 to the negative 3 newtons. You with me so far on that? Forces have to balance both x and y if it's at rest. If it's at rest, the forces have to balance. The downward force is 2.45. The upward force has got to be 2.45. Therefore, the y component of the tension is 2.45. Now I have the angle right here, 20 degrees, and the adjacent side of the triangle. I want to find the electric force, but that's the same as the x component of the tension. So let's say tan 20 degrees is equal to the opposite side, the x component of the tension, divided by the adjacent side, which is the y component of the tension, 2.4525 times 10 to the negative 3 newtons. So x ends up being equal to x component of the tension, and therefore the electric force ends up being equal to 2.4525 times 10 to the negative 3 newtons times tan 20. 8.926 times 10 to the negative 4. 8.926 times 10 to the minus 4. All right, so let's take a look now. We're looking for the electric force exerted on the pith ball by the charged Van de Graaff generator. Well, we just found the x component of the tension, but we know that since it's the only force to the right, it's got to balance the only force to the left, which is the electric force. So our answer is going to be C here, 8.9 times 10 to the negative 4. All right, let's spend a couple of minutes now just checking over what we did yesterday, along with the homework that we had yesterday. We had a few terms that we defined yesterday. We talked about electric potential energy. We talked about electric potential energy difference. We talked about electric potential. We talked about electric potential difference. We also talked about this other concept called work, which I'm not going to put up on the board here right now, and you'll see why in just a second. You guys remember what electric potential energy is? That's the big one, right? The big definition, the most general definition that we have here. If we think back to the analogy that I gave you yesterday of me going to the bank with my son, okay, we got $346 in change. The $346 total would be analogous to the electric potential energy. Electric potential energy is the energy that's stored in a system of two charges a certain distance apart. It's not per person, it's not per charge, it's the total energy. The total energy stored in a system of two charges a certain distance apart. Now the symbol for electric potential energy is E. Don't get that mixed up with the electric field. Remember I told you when you did electric field, make sure you put the arrow over it so you don't get it mixed up with energy. Potential energy difference, well, that's going to be delta E, right? It's quite simply the difference in electric potential energy. If you've got $346 now and you have $342 in 5 minutes because you went out to 7-Eleven and bought something, then your potential difference, your electric potential energy difference would be 4. It's the difference in electric potential energy. It's the final potential energy minus the initial potential energy. Now, we introduced another term yesterday, or reviewed another term from Physics 20 yesterday, that means the same thing as electric potential energy difference. Remember what it is? What is that term? What is that term? Starts with a W. Work. So the change in electric potential energy is equal to work. And of course, work is also equal to F times D. Remember that this force and this displacement have to be in the same direction as each other. If they're not, there's no work done. Okay, if the displacement is to the right and the force is upwards, there's no work done. If the displacement is upwards or downwards and the force is upwards or downwards, then there's work done. Electric potential. If we go back to the analogy again, $346 and change between the two of us. Okay, that was the total energy between the two of us. The energy per person, or the money per person, was $173. Electric potential is analogous to the money per person, except it's not money per person, it's energy per charge, or energy per Coulomb. Electric potential is given by the symbol V, and we can find it by saying it's the total energy divided by the amount of charge. The total money divided by the amount of people, right? E over Q. Of course, the symbol, the units for potential, electric potential, which is also known as voltage, are joules per Coulomb, or volts. Finally, electric potential difference. Potential difference given by the symbol delta V, because it's a difference, right? It's a change. It's the difference in energy per charge, the difference in money per person. We got $173 each. We go to 7-Eleven, we spend $2, got $171 each. Now, total, because it was two of us, we spent $4. We spent $4. The difference in energy was 4. The difference in potential was only 2, though, because each one of us only spent 2. Okay? Electric potential difference is the difference in energy per Coulomb. Now, there's 2 ways we can find that. It's VF minus VI, which, by the way, that equation is not on your data sheet. Okay, but it's pretty intuitive, right? But there's also delta V is equal to delta E over Q. That is on our data sheet, delta E over Q. Units for that, of course, joules per Coulomb, and of course, we could also use volts for that. One final term, an electron volt. That's a unit. A unit of what? Units per second measures speed. Joules measures energy. Watts measures power. Meters measures distance. Electron volts measures not exactly, but it's energy. Okay, you're right about that. It's energy. It's defined as the energy that's gained or lost by an electron as it goes across a potential difference of 1 volt. So the electron, let's see, most batteries are 1.5 volts, right? But let's say you got a 1 volt battery. Okay, the energy that's gained by the electron as it goes from one terminal to the other would be 1 electron volt. That make sense? The energy gained or lost by an electron as it goes across the potential difference is equal to 1 electron volt. Now, 1 electron volt in joules is 1.6 times 10 to the minus 19 joules. And there's lots of times where we're going to have to convert back and forth between electron volts and joules this year. My suggestion is set up a ratio. 1 electron volt over 1.6 times 10 to the minus 19 joules equals, if you're looking for the number of electron volts for 3.2 times 10 to the minus 18 joules, set it up like that. If you're looking for the number of joules given 6 electron volts, then set it up like that. All right, a couple questions for homework last night. Page 565. Let's take a look at those 2 questions now, please. Any issues there? Good? All right, let's do one more example then before we introduce our last topic of the unit here. This is on page 566. It says a small charge of 3.2 times 10 to the minus 19 coulombs. It's like 2 electrons, or it's like an alpha particle, right? 2 times the elementary charge. It's moved between 2 parallel plates from position with an electric potential. Be careful here. It might not even be a bad idea to underline that in red. It's not as important as some other things that we have, but I've underlined that in red because I want to distinguish between potential, potential difference, potential energy difference, work, right? There's a lot of terms that sound alike. This is electric potential to another position with this electric potential. Now, this question should have up on the board here, what's the potential difference between the two plates? So we're looking for delta V. Okay, and it also asks Jesse for what?
The electrical potential energy gained.
Okay, the electric potential energy gained. So we're looking for delta E there. Or you could call it, what else could you call it? Delta E is equal to? Remember the world's easiest question yesterday? Work, yeah. So you could say delta E you're looking for, or you could say W you're looking for. Now, delta V is the easy one, right? Looking for the potential difference. If you've got the initial potential and the final potential, just subtract them. 4.0 times 10 to the 3 volts. Subtract 2 times 10 to the 3 volts. My answer for potential difference will be 2 times 10 to the 3 volts. There's the first part of it. Now, we're looking for the gain in potential energy. Be careful here. It's not 2 times 10 to the 3. That's the gain in potential. The gain in potential energy is going to be found by using the other equation for potential difference, rearranging it, and getting Q times delta V. So the charge here, we're given as 3.2 times 10 to the minus 19 times the potential difference. Not the potential, not this 2 times 10 to the 3, not this 4 times 10 to the 3, but this potential difference of 2 times 10 to the 3. Multiply those together, we should get 6.4 times 10 to the negative 16, and the units would be joules for that. Now, let's convert that to electron volts. Okay. We don't necessarily have to in this question, but some other question maybe we do have to. 6.4 times 10 to the minus 16 joules is how many electron volts? Well, we know that 1 electron volt is 1.6 times 10 to the minus 19 joules. And X electron volts is 6.4 times 10 to the minus 16 joules. So let's solve for X. The 6.4 goes up by multiplying, and then we divide 6.4 by 1.6, and we end up getting 4.0 times 10 to the 3, I think it is. 4.0 times 10 to the 3 electron volts. Is that okay? This part of it is easy, ridiculously easy. This part of it gets a little bit harder, not so bad. This part of it, because we've never done this before, this conversion of electron volts to joules, maybe a little bit tricky. Make sure you can do that though, because we're going to have to do that. I promise you on your test, you'll have to do that. All right, try these two questions, please, on page 566. All right, let's take a look at number 2 here. It says an electron moves between 2 positions with a potential difference of 4.00 times 10 to the 4 volts. What is that? Okay, is that E? Is that delta E? Is that W? Is that V? Is that delta V? What is it exactly? What is it? Delta V. It's potential difference, which is delta V. We're looking for the potential energy gained by the electron. We're looking for delta E, or you could say we're looking for W. Probably call it delta E because that's the way the equation appears on our data sheet. Now, it's not a bad idea to draw attention to the fact that this is an electron. Maybe even write down that we know the charge and the mass of the electron. I'm not going to write down the numbers because they're on our data sheet, but it reminds me at least that I can look on my data sheet to find Q and M if I need them. All right, we're going to say delta V is equal to delta E over Q. Rearrange that to solve for delta E. It's Q times delta V. Okay, we get 1.60 times 10 to the minus 19, because that's the charge of the electron from our data sheet. Delta E is, delta V, I should say, is 4 times 10 to the 4 electron, 4 times 10 to the 4 volts. When we multiply those together, we should get 6.40 times 10 to the negative 15 joules. Is that right? Is that good? All right, now we got to convert that to electron volts as well. So let's do that now. We know that 1 electron volt is 1.6 times 10 to the minus 19 joules. We know that because that's what it says on our data sheet. On the left-hand side of our data sheet, it says 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So you don't need to remember that. X electron volts is 6.4 times 10 to the negative 15 joules. Solve for X. Okay, we take the 6.4 out by multiplying, divide it by 1.6, and look at what we get. 4.00 times 10 to the 4 electron volts. It's the same as the potential difference. Is that a coincidence? No, it's not a coincidence. But will it always be the same? No. It wasn't the same in the sample question we did, but it is the same here. So when is the potential difference going to be equal to the electron volts? And when is it not going to be equal to the electron volts? Good. This question involves an electron. Okay, the electron volts, the energy in electron volts will be the same as the potential difference in volts when you're dealing with an electron. But when you're dealing with something other than an electron, like an alpha particle or something with a charge other than 1.6 times 10 to the minus 19, then the potential difference in volts will be a different number than the energy in electron volts. My suggestion for you would be, look, if you're looking for the number of electron volts, find it this way, each and every time. If you remember that it's the same, that's fine. But listen, if you try to remember all these tiny little things, you're going to forget some of them, right? Be able to figure it out. And then figure it out like we did. And then after the fact say, oh, yeah, shoot, I could have just said it was the same number. So we just took 30 seconds extra time. It's not a big deal, right? That's not going to cause you to go over time on your diploma exam. Okay? Yep. 40.0, okay. Yeah, Rucker says would 40.0 kilo electron volts be a correct answer? Would it be correct? Sure. I mean, I would think, Rucker, generally, if that's a multiple choice question, that's probably not going to be one of your options. Probably this would be your option, but it's possible. Okay, that's okay. That's a correct answer. It just might not be one of your options, that's all.